Hello, calculus student. This video is for chapter 4.1, part 3, and we are working on problems that related to cone, like water tank, conical water tank, and water being pumped into the tank, and also being released from the tank. And we want to find the rate of change of the water level, because when we have, say, it's a water tank that is conical in shape, and so you have water that being pumped into it at a rate, and of course the water level would rise, but not in a constant way, because what happened is this is not a cylinder, so we want to figure out how water would be rising at a certain time. So let's read this question. It's a very typical question in related rate. An inverted conical tank has a height of 2 meters, so this is fixed. So we don't have to say x and y because the tank itself is 2 meters. We say 2 meters and then a diameter of 1 meter. So diameter, but instead of having write the diameter, I want to write down the radius is 1/2 of a meter. Water is pumped in the tank at a rate of 500 cm cube per minute. Now notice we were doing meter earlier as a measurement. Now it's changed to a centimeter. So maybe we should actually change to centimeters to the smaller measurement. So 2 meters is 200 centimeters. So let's change all of them to, and then half is 0.5. So that means half of a meter is 50 centimeters. Okay. And then we know that the water is pumped into at a rate of 500 cm. So all these water will become the water here, which is a volume of another conical that has a different height. So the height here changes. And the radius here also change. We would use H and R to denote this. The original tanks 50 centimeter and 200 centimeter does not change, but H and R of the water does change. What is the rate of change of the height of water level when height of water level is at 1.5 meters? So when it is rise to 1.5 meter, how is the height changing? It should be slowing down a lot because it's wider, right, at the top. So we want to know dx dt. So we know the water level is pumping in as 500 centimeter cube per minute. And that becomes the water here. So we say V dV dt is known as 500 when the height is 1.5. When H is 150, we would say. Okay. So what is the rate of change of the heights? So we need dx dt. Okay, and that. So this is the analysis. The picture is all those variables that we know. And so of course if we know dv dt and we need dx dt, we need to relate v and h. But there's a third variable r. Okay, so let's see how we can deal with it. Let's just write something that relay V and H. So the volume in a cone is 1/3 pi R square H, right? Now if I do dV dt and dx dt here, my R is changing, right? So I don't have dr dt. So unlike the Pythagorean theorem that we deal with in the last video, we know dr dt also, then that's no problem. But in this particular case, R is changing, but I don't have dr dt, so what should we do? We should replace R by H. Okay, so R, how do I relate R and H now? R and H are actually related to the original cones in a similar triangle. So if you look at a triangle, like the big triangle of the cone, half of the cone, you have 250 as the radius, and then the water, should be like this, should be the same one. The water is H and R. So we lay H and R, we would say 50 over R is equal to 200 over h. So that means 50h is equal to 200r, or r is 1/4 of h. If you divide 200 on both sides, 1/4 of h. So this is what we use. So this is used a similar triangle. This question is very popular because it involves similar triangle as well as volumes of conical shape things. So this tests you a lot of stuff. So now we would have a new formula of V equal to 1/3 pi r. We don't do r, 1/4 h square times h, right? So it become 4 squared 16. 16 times 3 is 48. Pi over 48 h cubed. So this is V. Relate V and h. And then we do dv dt, which is very easy to do. Would be pi over 48 times 3h squared. So this derivative is super easy. dx dt. After you cancel, we would have dv dt. 3 and 6, 48 cancel, would be pi h squared over 16 dx dt. So what is V? We have 500 pi over 16. What is H? H is 150. 150 square dx dt. So our dx dt would be having all this divided by 500 divided by all of this on the other side. So it'll be divided by pi divided by 150 square times 16. And if you plug everything in, dx dt would be rising at 16 over 45 pi. Over 45 pi. That would be 0.1132. 16 over 45 pi would be 0.1132 cm per minute. Okay. The second question is similar. It's also an inverted conical tank. It has a height of 20 feet and a diameter of 12 feet. So we draw the same question. Draw the same picture. This is fixed. 20. And the diameter is 12. That means the radius is 6. We like to do the radius because when we write V is equal to 1/3 pi r squared h is related to r, not the diameter. So that's why we like this. And then the water is leaking out of the tank into the tank. I think it's out of the tank at a constant rate of 5 feet per minute. So there's some water that goes out. If the height of water level is changing at a rate of 1 feet per minute when the height of the water is 15 feet, what is the rate of water that are pumped into the tank? So there is some water that is pumped in the tank, which is V in, so that it maintains some water here. And then they say that the water level is changing at a rate of 1 feet per minute. Wow, 1 feet per minute is very fast. So we say we actually know dx dt. Oh, I don't think I have enough space here. So we will have dx dt is known and is equal to 1. What we do not know dv dt. Equal to what? Okay. So just like before, we have to relate r and h first. So let's say, so this is r, it is changing, h is changing. So by similar triangle, 6 over r equal to 20 over h, right? So this is h, they look alike, h. So if you cancel them, then you will be 28r equal to 6h. R is equal to 3 over 10h. Put it back in here, so we have, so this is just relating R and H. 1/3 pi R is 9 over 100 because R squared. H squared times H. You square both sides, so you have R squared. So combining things together, so this is 3, so it's 3 pi, simplify 3 over 100 h cubed. But we need to relate dv dt with the h dt. So dv dt would be 3 pi over 100 times 3h squared dx dt. Okay, so we're almost done. So would be dv dt equal to 9 pi over 100 h squared dx dt. So we related the both. Now, so we have, what is the rate of water that is pumped in the tank? So we need dv dt. So what would that be? We just multiply this together, dv dt. The V is actually the volume of the water here. Okay, so dv dt would be equal to just multiply 9 pi 100 times, what is h? H when it is 15 feet. And then dx dt, they say dx dt is 1. Right. So basically we just do 9 pi, oh, actually this is a square. I have to do a square. So you multiply all of them together, it will be 9 pi times 225 over 100. Simplifying them, it will be 81 pi over 4. 1 pi over 4. So this is around 67.617 feet per minute. No, feet cube per minute. But now these are these are because you have something that's leaking out. So V in would equal to compensate what has leaked out, 17. You have to add the 5 feet per second that is leaking out. So it would be 63 plus 5, 68. Oh, 63, it should be 63. I put 63.617. Should be 63, not 67. So it would be 68.617 feet cube per minute. That would be what you need to pump in to keep this particular water level at that feet.